the field pattern, or why is the field uniform near the surface of the Earth? No? Then can you explain to me why is it that why the gravitational field near the surface of the Earth is constant? So back in our AS, when we did our projectile motion questions, right, we always took G as how much? Minus 9.81, right? And it was same everywhere. But the further you go away from a planet or any mass, right, G is supposed to be more or less, right? So when we do our math, we don't really bother about that. We take it to be constant, right? Why is that so? They appear to be parallel. Correct. So the change in distance is not that large, right? So the basic idea is that you can diagram show. So if you look at the lines here, the broader picture, you'll notice that the field lines are actually moving further away. Okay, and that is normal. Why? What is happening to the strength? The strength is decreasing. But if you look at the surface of the Earth, right, and I showed with this example here, I'm going to এই জায়গাটা হচ্ছে ছবি নিলাম. I took that small part there and I zoomed it up like that. So if you look at these lines here, they do appear to be what to each other? Parallel, right? But if you go further and further away, the change becomes more prominent. So very close to the surface of the Earth, your lines are parallel. And what does parallel field lines indicate? A uniform electric field or uniform field, any kind of field, right? So that's the reason why the G value is constant at this point. However, let's say you had a device that had a precision of 6, 7, 8, 9, 10 decimal places, like very precise, right? And I moved that device here to see how G changes. Do you think it'll change? Yes. Okay. The change is so negligible. We can do a math that we're going to love now because it's time consuming. But if you try yourself, take a distance of 10 meters and see how G changes. We'll learn a formula for G. You'll see in your calculator, it doesn't change. Your calculator shows 9 decimal places, right? But if you take, like, let's say a calculator online, take 20 decimal places, you'll start to notice the changes. It's a very small change. And that change becomes prominent when you go distances of 1,000 kilometers up in the atmosphere. Often it becomes like 9.8 and 9.7. So do you know there's this thing that goes around the Earth called the International Space Station? People go and stay there, right? Or taking the 110 kilometers above us. You know the value of G is there. It's actually 9.805. It's very, very negligible at that change, right? But then do you know why people float there? Yes. Can you elaborate how? Like they float around, right? And they call it 0G, but it's not 0G actually. True, but don't they appear like they're floating in zero gravity when they're in space, in that International Space Station? Aren't they floating around, right? So that means there's no gravity action on them. So how is that possible? Because G is 9.81. Asha, Amboli, do you guys remember we discussed this, that if you want to lose contact with the surface, what should your reaction be? No, this normally, if I'm not in contact with the surface, what's my reaction force? Yes, or online evolution is 0. So the moment the contact force is 0, what are you doing? You're floating, right? Or International Space Station, the reaction force is 0. Why? All the weight is used for what motion? Circular motion. So if all the weight is used for circular motion, right, how much do you have as a reaction? 0. That's when they're actually moving with the space station. So space station দুইজন একসাথে move করতেছে, তো দেখতে মনে হয় যে they're floating around. They're constantly falling towards the Earth. Okay? আচ্ছা, এটা just একটা extra discussion ছিল. এটার একটা math হচ্ছে ও AS এ থাকে. Let's say you're in the lift. লিফটটা নিচে পড়তেছে at 9.81. তুমিও লিফটের ভিতরে, you're falling at 9.81. What will you feel? Will you feel force on the lift, or will you start to float? You'll start to float. এটা হচ্ছে ওই যারা অ্যাস্ট্রোনটরা হচ্ছে ট্রেনিং করে for 0G, there's actually a plane. প্লেনটা কি করে? It goes very high up in the stratosphere, তো প্লেনটা ফ্রি ফল করে, and প্লেনটা যখন ফ্রি ফল করা স্টার্ট করে ভিতরে সবাই কি করা স্টার্ট করে, float. ওই যে some people want to experience 0G, they actually go and do that. Okay, so anyways, just to clarify করাই নিলাম. Right, so why is the field near the surface of the earth constant? It's because the lines are parallel, or they appear to be parallel, and parallel lines represent a uniform field. So that's the reason why they experience a constant value of G. Okay, so this is what we did to last class. Field lines draw করা হয়ে গেছে. So আজকে যেটা আমরা করবো is to clarify. Do you see how the lines are through your house? So you'll notice the lines are what to each other, parallel, right? But these lines are ever so slightly what to each other. Take a very, very precise instrument to measure the separation of these lines. And if lines হলো পাশাপাশি আনবো, এখানে তো obviously draw করতে দেখাই নাই। When your lines হলো পাশাপাশি আনবো, you'll notice that there is a what between these two. মানে এখানে তো দেখানো possible না? Yeah, there's actually a slight angle out there. And as you go further and further away, this becomes more what? Prominent. Okay, so that's basically why it appears to be zero near the surface, zero not constant near the surface of the earth. Yeah, right. I think we have clarified everything here. I'll just go to the points here. The direction of gravitational field represents the field lines. So field lines, they represent kora hoy. Field lines around a mass are radially inwards. Radial মানে হচ্ছে যে rays of a sun এর মতন দেখে radius এর সাথে. Gravitational field lines are uniform, where the field strength is same at all points. The lines are equally spaced and parallel. Field lines on the surface of the earth. Okay, so that's what we have seen so far. So আজকের topic to start করি. So here's the Newton's law of gravitation. How do we measure gravitational field strength? So there's a way to measure the field strength. So OJ chapter. Okay, so what is this 13.2? So আমি just একটু আগে গিয়ে তোমাদের checklist করে নি, দেখে নি if we have covered everything. So understand that gravitational field is an example of a field of force, and define gravitational field as a force per unit mass. So if they ask you in your exam, what is a gravitational field? It's a region in which a unit mass experiences what? Force. Okay, and represent gravitational field lines by means of field lines, right? So এটা হয়ে গেছে. So these two are done. We're done with 13.1. এখন আমরা start করতেছি the 13.2, which is gravitational force. Right, so it's a background that this one is what Newton is generally credited for, the mathematical discovery of gravitational field. So what did he figure out? So what he found was that when you have any two masses, right, any random two masses, there's no particular need for this mass to be of any type. Any kind of mass is fine, big, small, uniform, non-uniform. If there are any two masses out there, Newton realized that the masses apply what on each other? A force. And he named that force the force of gravitation, and this whole concept was called gravity, right? So this gravitational force between these two masses, right, follow what law? So it follows the Newton's third law pair, right? So what should the properties of these two forces be? Let's call it F1 and F2. So F1 and F2 property look here. These are masses. This is M1 and M2, two masses. There's a force of attraction between them. So last class I বলছিলাম তোমাদেরকে that the force is exclusively what only? Attraction. Gravity can repel করতে পারে না. It's one thing that gravity can't do. It can't repel. If you think of electrostatic forces, electromagnetic forces, they can repel, but gravity can't, right? So it's an attractive force out there. So what are the properties of these forces here? So number one, they must be of what magnitude? Equal magnitude. Because you have to understand, Newton already has established Newton's laws, the three laws. So he was trying to apply those onto this idea. So equal magnitude, তারপর কি হওয়ার কথা? Same type of force, so they're the same type. Then same line of action, which means they act at the same place, line of action. And the fourth one is same. কি ছিল মনে আছে? Same চারটা জিনিস হয়, right? So what's the fourth one? Same direction. Duration, right? Direction, same duration. Then what's different about them? Yes, opposite direction. So যা বলতেছি সব কিন্তু এখানে ম্যাচ করতেছে, opposite direction. And lastly, what was the feature? The most common source of mistake. Must act on signal. Different bodies. Okay, so the forces must be on different bodies. So yeah, if you look at the forces that has been established here, you'll find that all of these do actually, satisfy these points here, right? So this force was called the force of gravitation. And what Newton found was that this force had some properties. So what did he figure out? So the first thing he figured out was this force that you see here is actually directly proportional to the mass. Which mass? Not M1, not M2, but both. So the force of attraction is directly proportional to the product of the masses. So I'll give you a simple example. Let's say I have 1 kg here, right? And 1 kg here. For the mass connector force. Okay? আমি যদি এটাকে 2 kg করে দেই, ফোর্সে কি হবে? সেম থাকবে না বাড়বে? বাড়বে। কিন্তু ফোর্সে কি 2 kg 1 kg এর উপরে বাড়াবে নাকি 1 kg 2 উপরে বাড়াবে নাকি দুজনের জন্যই ফোর্স বেড়ে যাবে? Because Newton's third law of air says that the force must be equal, right? So আমি যদি একটা mass বাড়ায় দিই, force টা বাড়বে, but force কিন্তু দুজনের মধ্যেই বাড়বে. So the idea is that if you have two masses like this, right? This mass and that mass, and you increase one of the masses, বাড়ায় দিলে এটা, দুইটা ফোর্সই বাড়বে. And that's because the force between them depends on both the masses together, product of the masses. Okay? So it's not like যে একটা বাড়লে ও খালি বেশি ফোর্স দিবে, that the third law of air কাজ করে, because one can't be more than the other. Okay, so is it F1 or F2? So this force is both mutual force. This force that you see here is both of them, and both of them will have equal magnitude, right? So it's basically both the masses that we are discussing here. Okay, so yeah, the first thing is that the product of the masses force is directly proportional to the product of the masses. Yeah, I intend to change for the product of the masses. And the second thing that they found was this force is inversely proportional to the square of distance separation. So according to Newton's law of gravitation বলা হয়, he found that the force is directly proportional to the product of the masses and inversely proportional to the distance of separation. So a couple of points here. A full concept has some assumptions out there. Assumption হচ্ছে masses are considered to be what masses here? Last class বলছিলাম. What did we assume the masses to be? The masses are assumed to be yes, very good. Online যারা বললা, point masses. So আমাদের কিন্তু হচ্ছে we consider forces acting from the center of mass. Masser আশেপাশে কি হচ্ছে, size কিরকম, shape কিরকম is not our concern. So first হচ্ছে point mass. Our secondটা হচ্ছে distance d is the distance between what? The surface of the masses, or is it the distance between the center of the masses? Center of masses. Okay, because since we are considering them to be point masses, the force will be acting on the center of masses. So d is the distance between the center of masses. Right, F is directly proportional to M1, M2, and F is inversely proportional to 1 by d squared. So that's the Newton's law of gravitation. It is flawed. আচ্ছা, এই লটাতে অনেক ফ্ল আছে, আমি ফ্ল গুলো এখন দেখাবো তোমাদেরকে। কিছু লেখো না, বলি কি অনেক ফ্ল না, মানে there were some issues with it when we first found it. Okay, So according to Newton, when there are two masses, right, any two masses, what do they apply to each other? Just briefly recap kori. If there are two masses, right, what do they apply on each other? Force. And the forces of what nature? Repulsive or attractive or both? Only attractive. So right now, this remote and this remote, right, do you think they're attracting each other? Yes. Okay. Why don't they move towards each other? Yeah, it's very small. So Newton couldn't really explain why it was not prominent. He explained that planets can exert it very well, like Earth apply for it, but why isn't like a mountain doing it? Mountain is pretty big, right? So why aren't like small rocks flying to mountains? Or right? Or why don't we see other big objects, right, exert forces on very small object out there? So according to law of gravitation, right, if you're next to Mount Everest, which is massive, it has a lot of mass, and you have a small piece of pebble with you, it should be strong enough to attract it, right? But why not? So, those were some of the flaws he couldn't really answer, because the problem with the equation, he came up with an equation, by the way, and the equation was F is proportional to what? M1, M2 divided by what? D squared. But this is a relationship. This is not what an actual equation. Can I do a math using this? No, because there's a proportionality symbol there, right? And as you know, if you want to get rid of this symbol, you have to do something. What is that? Add a constant. Constant. So back when Newton was working with this for a couple of years, the constant was missing. So if you don't have the constant, you can't really have an experimental proof for what's happening. You can just say that, hey, দুইটা mass বড় হলে force বাড়ে. What's the evidence? Or distance বাড়ালে হচ্ছে force কমে. What's the evidence? So no evidence, right? So এখানে Newton got stuck. Somebody else came and helped him out, but I mean, portable to see. There's a question here. What are point masses? Let me explain. Point masses could be simple. Essentially, when you have a planet or a rock or anything for that matter, they're very randomly shaped. So this is like an asteroid, right? So eight are shaped non-uniform. And you have another rock somewhere else. Let's say there's another piece of rock here. And it's randomly shaped. So আমরা যখন math করব, we're trying to find force between these two, right? Questionটা হচ্ছে, where do we take our distance from, and where is the mass? So can you tell me, যে এই objectটার mass কোথায়? It's everywhere, right? But it appears to be acting where? At the center, and we have a name for that. What is it? Center of mass. So that point is the imaginary point on an object where all the mass appears to act. So আমি যদি এই asteroidটাকে এই shapeটাকে ignore করে, I just consider it to be a dot of that equal mass. Doesn't it have the same effect? Because এই চারিদিকে জিনিসটা তো just for visual implication. Visually it's like that, but where's the actual mass of this object? On average, center, right? So আমি simplify করার জন্য I'll remove this and consider that to be my asteroid. And I'll consider this center of mass to be the center of that asteroid. And then I can do my math just by using what? Rather, the center of masses. I don't need to worry about my shape and size here, right? So the assumption that we make is that all masses out there are considered to be what masses? Point masses. For simplicity, okay? And will that affect your math eventually? It doesn't. Because the gravity appears to act on the center of mass, right? So if you assume the whole thing to be just that point at the center, it will have the same outcome. It doesn't really affect it. Okay, so yeah, that's the reason why we assume everything to be a point mass. Does it have real life implications? So real life terminology assumption, it doesn't really impact our math. At one point, it does. Okay, so when they're launching, probes and they're making them land on asteroids. I don't know if you know this. They send these probes far out in space and they'll go and land on an asteroid, right? And there's this, astrophysics are one of the famous joke that they assume everything to be point masses. And যখন ওই ল্যান্ডারটা ল্যান্ড করতে যাচ্ছে, ও তো পয়েন্ট ম্যাসকে টার্গেট করে ল্যান্ড করতে যাচ্ছে। ওটা চারিদিকে কি থাকে? আরো ম্যাস আছে না? ওগুলো তো ক্যালকুলেশনে নেওয়া হয় না। তো দেখা যায় প্রবগুলো যে হচ্ছে মাউন্টেনের সাথে বাড়ি খায়, এটার সাথে বাড়ি খায়, ওটার সাথে বাড়ি খায়, because they're always trying to enter the what of the mass, center of the mass. So eventually, that's like, if we did our math to send a probe into space, the probe কোথায় যা ল্যান্ড করার চেষ্টা করবে? The center of that mass. But obviously, probe the center যা ল্যান্ড করবে, কোথায় ল্যান্ড করবে, surface. That's when the laws of gravitation will change. We don't learn that. আচ্ছা, তখন হচ্ছে mass গুলোকে আলাদা করে কনসিডার করা হয়, the shape and size consider So for our A-level purpose, we'll assume everything to be what? A point. Okay, for simplicity, okay. All right. So yeah, these are called point masses. Or temperatures. Oh, what does it mean? Yeah, so the thing is, that's the concept of center of mass, right? So I'll show you with this ruler. This ruler has mass where? Everywhere, right? But if I want to balance this ruler, I can place my finger here and it balances, right? But there's mass there. Why is it not falling? Gravity is W equals to mg, right? So gravity will only act where what acts? Mass, right? So center of gravity and center of mass, by the way, are interchangeable because wherever your center of gravity would be is the place where the what happens to be, the mass. So in this case, this is center of gravity, you're right. That's because this is also the what? Center of mass. But do you see it's balanced right now? But there's mass on this side, right? Why doesn't it fall? Like, why doesn't this side fall that way? You can be mass okay, right? Shouldn't it fall that way? But it doesn't. Why? Because there's equal mass on the other side. So it balances out, right? So eventually, do I need to balance these sides or I can just balance the center of mass and the thing will be balanced? Center of mass. So I can assume that all the mass appears to be acting where? There, right? But actually mass is there everywhere. This is just an assumption. So I can replace this scale. This is 200 grams. I can replace this scale with a dot of 200 grams. Wouldn't it be the same behavior? Because that's just a dot there, right? So I can interchange these two things. I don't need to worry about the shape because there are no consequence. Right? So that's why we work with only the center of mass. Right. So I hope you guys are clear with what center of mass is or point mass. So we assume this to be a single point where the mass appears to be active. Right. Okay, so coming back to my thing, the equation f is directly proportional to m1 m2 divided by d square. Okay, so the question is, how do we get the actual formula? Because I'm বললাম formula কিন্তু কাজ করতেছিল না. Like when Newton originally came up with the equation, there was no real proof of it. There's no experimental evidence of it. So what would you do? তোমাদেরকে জিজ্ঞেস করছিলাম. So you said that you would like to introduce a what here? Constant, right? So f should be equal to what if I want to introduce a constant here? মানে equal to যদি করতে চাই. F equals to k m1 m2 divided by d square. How do we find this k? No. If you simplify units, you'll find the unit for k, but the value. So what's the magnitude of k? কেমনে বের করা যায়? So এটা হচ্ছে m. Right. So if we know the value of f, m1, m2, d squared, then we can find the value of k, right? Can you give me an example where you know the masses and the force and the distance? No, it's not there. So back in the time, right, when they did the experiment, they didn't even know what the mass of Earth was. So actually, not the mass of the core type, but back then they didn't have this, right? So how did they actually come up with the answer? So it's an interesting story. So there's this person who did this experiment. Ingenious device setup create to get the value. It was by mistake, by the way. He didn't really intend it to be, but he eventually realized that K বের করতে পারবে. So our experiment ছিল, he took a very tall shed. Farm shed থাকে না? They store grains in it, right? So UK he took this shed and it's very tall. And he was doing an experiment to find effects of Earth's movement on oscillation, which itself is a very famous experiment. যে কি করবা? একটা very long rope থেকে তুমি কি হ্যাং করবা? একটা mass. And apparently, as the Earth's rotating, right, এই massটা over time কি করা start করবে? Wobble করা start করবে. So mass এরকম আছে. And it's a very long rope. So subtle movements keep that. the longer your rope would be, wouldn't the smallest movements be very visible? So the idea was that if you allow this to be there for long enough, it'll start to do this. And that rotation can actually help you figure out how the Earth rotates. That's a completely different science. But while doing this experiment, he found there was a problem arising every time. Problemটা হচ্ছে, whenever he tried to do the experiment, he set up this long rope, like 3-story tall rope. He found that the rope was always tilted, and he thought maybe the ceiling is tilted, but ceiling tilted থাকলে কি rope tilted হবে? No, rope to still straight down a little, right? So every time he tried to calibrate it, he found that there's a small tilt, and eventually, as it goes, right? I mean, like are these stories for dramatic effect? I don't know, but he found that right next to the shed there was a very large iron ore, like a mountain made up of entirely what? Iron, right? And this mountain has a lot of what? Mass and iron tonic dense. So because it's dense, this particular volume was very massive, right? Very heavy. And this mountain was actually applying what on that rope there? Gravitational force. So he found that it was a hill, Hilter 9. They mined all the iron out now. So this hill was basically attracting the mass sideways. And that's when he realized, wait a second, I know the mass of this thing here at lead ball. So he knows the mass of this, right? He also knows the angle generated here, very small angle, theta. So, and it was an equilibrium, right? So can you tell me if my system is like this, right? Where the mass is like that, and mass to equilibrium and the angle here is theta. Can you tell me what should the force value be here? Yeah, so it will be t thake, this is going to be t sine theta, right? That's the force acting that way. And then he realized that you can find the force using basic mechanics here, and you can estimate the what of this mountain. Mass. Estimated the mass. Estimate course of mass and body. Right? Remember estimation? Right? So how would you estimate this mass? What would you do? It's a hill, conical hill. Right, so you first find the height of this hill, and then you will use the base area to find the what of this? Volume, very good. And then this is primarily made up of what? Iron. So density equals to mass by volume, and you can estimate the what of this mountain mass, right? So eventually he found the mass of this mountain, M2, and orthoe mass already jana, which is M1. And he found the what between these two, his shed and the mountain distance, right? Where would you take the distance from? The surface of the mountain or the center of the mountain? Center of the mountain. Obviously, like into খুবই বড় assumption করা হচ্ছে, but আমি দেখাই কি করে eventually. So D আসে এখান থেকে. And he put in his values, right? M1 জানে, M2 জানে, D জানে, F জানে. And eventually, by doing the math, he found that the value of K is 6. Approximately 5.9 into 10 to the power minus 11 Newton meter square per kg square. This was the constant K, and that was one of the reasons why Newton failed in finding it. Is it a very large value or is it a very small value? Extremely small value, and that's the reason why if you take a remote and another remote and try to find the attraction, right? Do they attract? Yes. But if you do your math, the attraction is to the power 10 to the power minus 21. But the force is something into 10 to the minus 21. Will they move? No, right? But they try to move. Who's stopping them? Friction, gravity, my hands, right? But here's the interesting thing. Imagine these two remotes were floating in space, isolated, away from everything in the universe. What will they do? They'll start to move towards each other, right? Will they move very fast or it'll take time? It'll take awfully long time. But will they eventually reach together? Yes. And that's the birth of what? Stars. Stars are born like that. So stars there are billions and trillions of random what floating around in space? Gases, protons, right? And over billions of years, these protons start to what towards each other, move towards each other. And as they're moving towards each other, force যেহেতু, what are they doing? Accelerating, and they're gaining what energy? Kinetic energy, and eventually after a billion years, they come and collide, and all that K turns into what? Internal energy, and the star gets its energy from there. Okay, so anyways, that's the other part of our topic. So we finally have the value of K. A K টাকে হচ্ছে পরে replace করে একটা symbol দেওয়া হয়. So finally, the formula for your gravitational force of gravity is equal to a quantity যেটা এটাকে নাম দেওয়া হয় capital G. আচ্ছা, small g আর একটা quantity আমি সবসময় বলবো capital G, m1 m2 divided by d squared. This is the equation. Okay, this is the formula that helps you find the what between two masses, gravitational attraction between any two masses out there. I'm going to try to find the gravitational attraction between random masses out there to see careful values there. Okay, so are you so far clear about the formula? Formula to key. Now there's a small catch here. Formula এখানে minus there. So there's a minus in the front of the equation. Okay, we need to learn what the minus represents. I'm a bit horrible to see, but are you okay with what's there so far? That's the formula. আচ্ছা, a mountain থেকে কি g আসছে সেটা জানা দরকার নেই। I'm just giving you a background as to how small this value is. Okay, eventually there's a person called Cavendish. সেই এক্সপেরিমেন্টটা করে g এর ভ্যালু সবচেয়ে অ্যাকুরেটলি বের করে, and this thing is a math that তোমাদের কোশ্চেন পেপার আসছিল, মানে ওরা ডেটা দিয়ে দিছিল। সো ক্যাভেন্ডিশ কি করছে, যে দুইটা স্ফিয়ার দেখতেছ না এখানে, এই স্ফিয়ার গুলো দে আর মেড আপ অফ lead, আর ওই যে বলছিলাম না যে ফোর্স থাকলে দে আর সাপোজ টু মুভ, সো দিস ডিভাইস ক্যান মেজার ভেরি স্মল অ্যাঙ্গেলস। সো ইভেন্চুয়ালি এই ডিভাইস দিয়ে খুব অ্যাকুরেট ভ্যালুটা বের করা হয়। ওকে, সো এটা আমাদের লাগতেছে না, জাস্ট গেভ ইট হিয়ার টু নো দ্যাট, টু শো যে কেমনে আসছে অ্যান্সারটা। বাট ইয়া, দিস আর দি ভ্যালুজ, লেটস রাইট দেম ডাউন। So G তে কি represent করে? It is called the universal gravitational constant, and the name kind of gives it away. Universal মানে কি mean করে? It is the same value কোথায়? Everywhere in the universe, which is very important. You know why? Because আমরা যখন হচ্ছে আরেকটা স্টারে, আরেকটা গ্যালাক্সিতে, we're trying to figure out what the black hole is doing there. ওখানে যদি G value different হয়, wouldn't our math fail? But it doesn't, because the value of G is what everywhere. Any place in the universe you go, G is the same, which is not true for any other constant in physics. But this is one true universally constant out there. যেখানে যাবে it's the same. Okay, from the event horizon of a black hole to the farthest reaches of the universe, সব জায়গায় এই ভ্যালুটা সেম। ভ্যালুটা কত তোমাদের মেমোরাইজ হয়ে যেতে হবে eventually, 6.67 into 10 to the power minus 11 Newton meter square per kg squared. Okay, এটা এতবার ইউজ করতে হবে, so I don't think you should refer to the booklet all the time. তোমরা এটা মেমোরাইজ করে ফেলে বেস্ট হয়। It is. We'll see. So there's a formula out there. That formula works outside the surface, but if you start to go inside the surface, the formula is different. So right at the center, you get a value of 0. So that's the next topic we do. Right, next is distance of separation. The distance. Right, so that's the equation that you have. So minus, by the way, এটা হচ্ছে for gravitational attraction, gravitational force. Right. আরেকটা হচ্ছে, what is the importance of the negative sign there? Sorry to explain করি। একটু দিকে দেখো নেগেটিভ কি মিন করে। সো এটা একটা ফিজিক্সের হচ্ছে কনভেনশনটা কোথা থেকে আসছে একটু এক্সপ্লেইন করি। লেটস সে you have two masses there, and these masses are charged, so plus, and arekta chip plus. And then you have two masses here, plus, and the other one is minus. Can you tell me what would these two masses experience, the plus and the plus? Repulsion. Okay, repulsion. And what would the plus and minus experience? Attraction. What would the minus and minus experience? Repulsion. Okay. Now, if I want to find the force, I'll multiply them to get their product. That's a force charge multiply. So if you multiply a negative number with a negative number, the product is going to be what? Positive, right? That's okay. You multiply positive with positive, what should that be? Positive. You multiply positive with negative, what should that be? Negative, right? So it turns out positive eventually turns out to be the value for what kind of interaction? Attraction or repulsion? Positive to the answer repulsion, and negative is outcome for what kind of interaction? Attraction. So এটা use করে ওরা হচ্ছে এখানে একটা নেগেটিভ সাইন দেয়। এই নেগেটিভ সাইনটা কোনো ম্যাথমেটিক্যাল ইমপ্লিকেশন নাই। We will ignore this when doing our math, but the negative is just there to explain the fact that the force can only be of what nature? Attraction. Okay, that's the only reason. Okay, so negative symbolic data. Negative is symbolic and only shows that the forces are attractive. Right, so there you go. এই জিনিসটা তোমাদের নোটসে না, এটা একটু কপি করে দাও। This is the law. 3 মার্কসের জন্য আসে Newton's law of gravitation. So Newton's law of gravitation কি স্টেট করে? খুবই straightforward. You just basically describe the formula. The law states that the force of gravitation is directly proportional to the product of the masses and inversely proportional to the square of their distance separation. So that's the Newton's law of gravitation. You'll ignore the negative sign for your math. Okay, we can note there. Ignore the negative sign for force related calculations. It works. It works everywhere. So that's the reason why they call it universal. There's no place where it doesn't work. So you can use it safely in any kind of scenario. Right, so ignore the negative sign for force related calculations. So তোমাদের ম্যাথের সময় তোমরা নেগেটিভ সাইনটা দিয়ে কিছু পড়া লাগবে না। You can just do it without that sign. Done. Do you have any questions? So it's very straightforward what I just explained so far of the complicated tissue 9. This is basically a formula that helps you find what? Force of attraction between any two masses. Like any two mass, anywhere, any two mass, you want to know what the attraction is. This is the formula. F equals to minus G mm divided by D squared. Okay. For our A levels, we make some assumptions. We assume the masses to be what masses? Point masses. So if it's a chair or a table or whatever the shape is, we just assume the center of mass to be where the force is acting. And that's about it. That's exactly what it is. And this is called the Newton's law of gravitation. So from the equation, can you tell me how does force relate to mass? Directly proportional. So if I have more mass, there'll be more force, right? And by the way, I think if there are two masses, okay, and M1, M2, 1 kg, 1 kg, there'll be a force, right? What if I make this one 2 kg and this is 1 kg? What happens with the force? Will it be same or more? It 1 kg to 2 kg column, it is still 1 kg. So would the force be same or more? More, right? But which force would be more? The force of the 1 on the 2 or the force of the 2 on the 1? Or should they both be same? Both should be same because this is Newton's third law, right? So if the force increases, both will apply more force out there. So student ki mone pore that Earth is applying 600 newtons on you. How much force are you applying on Earth? 600. Okay, so but the Earth doesn't move. That's because the Earth is heavy. But you're still applying the same force that the Earth applies on you, and it's equal and opposite. Okay. Mass. However, what inside a mass causes gravity? No one knows. That's a mystery. So we know all the effects of gravity, but we do not know the origin of gravity. Like what is there inside a mass that provides gravity? So that is still not clear. Okay, so a basic example here just to get familiar with the equation. Find the force of attraction between the Earth and Earth. Mass of Earth 6 into 10 to the power 24 kilogram. Mass of person to the sea. Radius of Earth is 6,400 kilometers. G, universal gravitational constant, 6.67 into 10 to the power minus 11 Newton meter square per kg square. So yeah, find me what's the force of attraction between the mass and the Earth, one of the person and the Earth. Right, radius, 6,400. Oh, sorry, kilometers of it. Thank you. কি আসে দেখো ট্রাই করে six 683, just 683. Yeah. Do you think it's too much or too little? No, so 686 Newton, right? is the force that the person experiences. What's the person's mass? 70. So can you find the weight of a person whose mass is 70? How would you find the weight? How much is it? 70 or 9.81. Do you actually found the weight? Yeah, because what is weight? Isn't weight the gravitational attraction of a mass on a person? So this is how weight is actually calculated. But eventually we simplified it to W equals to mg. Don't we need the height of the person since the distance would technically be from the center of mass? Yes, 6,400 kilometers, if you add the height of a person, right? What is the distance still going to be? I mean, the person's question is that radius of the Earth to the center of mass, the person is center of mass, right? Center of Earth to surface, which is 6,400. Well, you put a percentage to 1 meter, right? Does that really make a difference? No, right? So that's why it's not a problem. But yes, technically speaking, you need to include that as well. Okay. Yep, 684 Newton আসে so কেমনে করতে হয় 6.67 into 10 to the power minus 11 into mass হচ্ছে 6 into 10 to the power 24 into 70 divided by the separation because earth এর উপরে percent so the separation is going to be that radius so 6,400 into 10 to the power 3 করতে অনেক উপরে যাবা এটা মিটার নিতে হবে ওটাকে আবার কি করতে হবে square so once you put them all together the answer is going to be 684 Newton and that happens to be the weight of the person okay so this is also the weight do we always take D as 6400? No, for a person on the Earth, yes. Like because the center from the center of Earth to the surface is 6,400. So if the person is on the surface of the Earth, yes, you take it as 6400. It's actually not 6400. It's 6389 point something. This is to two significant figures. Right, so distance between those two, which is still going to be same, right? Because the person's size is very negligible, so it doesn't really make a difference. Right, so I think everyone's done. Any question? Comfortable the Bharat? Ask your question. So this is done, by the way. This is called Newton's law of gravitation. So I'll just quickly go through this. A gravitational force between two bodies outside a field between Earth and the Sun is defined as the Newton's law of gravitation. Recall that the mass of a uniform sphere can be considered to be a point mass at the center.